Look closely at the physical architecture of modern technology. From high-performance microchips to biocompatible medical implants, these devices rely on perfectly engineered, ultra-thin surface coatings. For decades, creating these exact nanoscale coatings has relied on a single foundational technique: conventional thermal chemical vapor deposition, or CVD. This diagram illustrates the basic thermodynamic mechanism of thermal CVD. Vapor phase chemical precursors are injected into a vacuum chamber. These gases flow over a flat substrate resting on a heated chuck, where extreme heat forces a chemical reaction to deposit a solid layer. By adjusting specific variables, engineers dictate the physical properties of the resulting film, driving up the absolute temperature, and carefully tuning the flow rate of the precursor gases directly determines both the uniformity of the film and its internal crystalline structure. The primary industrial application of this baseline model is metal-organic chemical vapor deposition, or MOCVD. MOCVD is a technique that uses metal-organic precursors to grow semiconductor and oxide films, such as gallium nitride and indium nitride. But this baseline model encounters a severe physical limit. As we attempt to coat thermally fragile substrates, like polymers, or structures with increasingly complex geometries, the application of extreme heat and a continuous vapor stream causes the materials to degrade or coat unevenly. Advancing thin film synthesis requires moving past the continuous thermal model. To deposit precise films on modern architectures, we have to systematically decouple and independently control three foundational reaction variables: energy, time, and phase. To build the next generation of nanoelectronics, engineers must stop relying on the ambient environment of the deposition chamber and actively engineer the physical interface at the atomic level. The first mechanistic problem we face is the temperature constraint. How can we trigger the high-energy chemical reactions required to form a thin film on a substrate that would melt or chemically degrade under typical thermal CVD temperatures? Returning to our chamber diagram, we solve this by utilizing plasma-enhanced chemical vapor deposition, or PECVD. PECVD is a modification of thermal CVD that uses plasma energy to activate chemical reactions at lower temperatures, effectively isolating the energy variable. This mechanism relies on energy dissipation control. We precisely direct plasma energy into the gas phase, causing high-energy collisions that break the precursor bonds. The activated molecules then drift down to bind gently to the cool surface without transferring destructive heat to the substrate below. This lowered temperature threshold allows engineers to deposit robust coatings directly onto highly sensitive organic materials. In modern applications, PECVD is utilized to deposit pH-responsive polymeric thin films. These specialized polymers react to changes in acidity and serve as critical components in biomedical sensors and smart coatings. Manipulating the plasma parameters provides direct control over the physical and mechanical properties of the resulting inorganic films, such as their density, hardness, and chemical composition. For example, by carefully tuning the flow of silane gas through specific plasma parameters, engineers can deposit silicon nitride films with precisely engineered tensile stresses. By decoupling the activation energy of the chemical reaction from the absolute temperature of the substrate, PECVD expands the catalog of viable deposition materials, from robust semiconductors to delicate, responsive biomaterials. The second major limitation of conventional CVD is spatial. Modern microchips feature high aspect ratio structures, which are deep, narrow, microscopic trenches etched into the silicon. This animation shows the physical failure state of continuous vapor flow in these narrow geometries. As precursor particles enter from above, they rapidly build up thick layers at the top corners, eventually merging to seal shut an empty void in the lower half. To isolate the time variable, material scientists rely on atomic layer deposition, or ALD. ALD is a specialized CVD variant based on self-limiting surface reactions that enables atomic scale control over film thickness and composition. Unlike continuous CVD, ALD relies on temporally separated reactions. When precursor A floods the trench, molecules bind to the walls to form exactly one atomic layer. Because the reaction is self-limiting, that layer physically rejects any additional precursor A particles from attaching. The ALD cycle operates chronologically. After pulsing precursor A to form a saturated monolayer, a purge removes the loose particles. Then precursor B floods in, reacting exclusively with the precursor A layer, followed by a final purge. Because the surface reaction stops itself once the layer is complete, the duration of the gas flow no longer dictates the film's thickness. The exact number of chronological pulses guarantees absolute atomic scale precision. Within this cycle, variables like purge gas flow rates and purge duration must be strictly calibrated. This controls the balance between impurity levels and the film's electrical resistivity, a critical calculation when depositing conductive materials like titanium nitride. This concept of manipulating time extends to broader techniques like pulsed CVD. Engineers utilize advanced methods featuring temporally separated pulses of silicon tetrachloride and ethylene. Sequentially pulsing these precursors creates superconformal silicon carbide coatings that continuous flow methods cannot match. This pulsing relies on a mechanism called surface site blocking. Timed pulses intentionally inhibit film growth in overexposed areas of the substrate, giving the chemical reaction in the underexposed areas time to catch up. These temporal gating methods are strictly necessary for depositing ultra-thin crystalline electron channels. Growing precise beta gallium oxide films is currently required to manufacture next-generation 2D metal semiconductor heterojunctions. By replacing continuous streams of chemistry with discrete, time-gated steps, engineers circumvent spatial shadowing and achieve mathematically perfect conformality, regardless of the underlying topography. Even with precise control over energy and time, conventional, plasma, and atomic layer variants all share a reliance on volatile gas phase precursors. This restricts material options and limits the types of chemistries that can be effectively delivered. To solve this, researchers manipulate the phase variable, integrating liquid phase deposition techniques directly into the CVD paradigm. This diagram details mist chemical vapor deposition, or MIST CVD. MIST CVD utilizes aerosolized precursor droplets to deposit metal oxides. An ultrasonic atomizer delivers a dense cloud of aerosol into the chamber, which settles onto a moderately heated substrate to form a uniform film. Delivering precursors in a liquid mist at lower temperatures significantly alters the film's morphology. It yields remarkably low dislocation densities, meaning the crystalline structure contains far fewer physical defects. This mist delivery mechanism ensures the successful growth of highly transparent, conductive antimony-doped tin oxide films, as well as high-quality alpha gallium oxide layers on specialized templates. Isolating the phase variable also enables specialized hybrid methods like initiated CVD or ICVD. ICVD is a solvent-free method for fabricating polymeric thin films with precisely controlled thickness and surface properties. This allows for polymer fabrication without the need for high temperatures or liquid solvents, granting the control necessary for regulated biomedical applications, such as drug release coatings on temperature-sensitive substrates. By shifting the delivery state from a pure gas to engineered aerosols and liquid hybrids, researchers bypass the strict volatility limits of standard thermodynamics to achieve complex multi-element stoichiometries in high-quality crystalline films. This synthesis matrix measures energy source, delivery time, and precursor phase. Thermal CVD and MOCVD sit at the zero coordinates: thermal, continuous, vapor. Shifting energy outward creates PECVD. Shifting time outward creates ALD. Shifting phase creates MIST CVD. Each trajectory solves a physical limit. Plasma controls tensile stress. Pulsed self-limiting reactions guarantee exact conformality, and aerosols reduce crystalline dislocations. By deconstructing and mastering the individual kinetics and thermodynamics of the deposition interface, material scientists transition from simple surface coatings to the precise engineering of the atomic scale interfaces that define modern electronics. Every breakthrough in nanoelectronics or smart biomaterials begins with a fundamental decision about how to manage energy, time, and mass inside a vacuum chamber.